This work deals with person identification according to his unique typing style. Today, in a digital world where all is done using computers and remote communication, the need for a solid identification method is arising. On top of that, the COVID-19 pandemic speed up the need for remote services. Here, Bob the banker is reaching Alice. Alice is interested in transferring money to her daughter's account. To do so, Bob requires the good old-fashioned password. Now, the problem is that Bob is transferring the money. He doesn't really know if that is really Alice on the other side, or it might have been that someone else got to her bank account details. On the other hand, Alice doesn't know if the person on the other side is actually Bob, or some other person claims to be Bob and now has all the details of her bank account. So, the missing ingredient here for a safe and trusted transaction is a solid identification method and even continuous identification. Person identification can be done using three different methods. Something the user knows, which can be a password. Something the user has, token for example. And something the user is, which can be his appearance, behavior, fingerprint, and so on. This work deals with something the user is approach. We can identify a user by his characteristics in three different ways. First, visual, an image, which is static-based, or a video, which contains motion information. Second, geometry, which means measurement of different body parts. Last, behavior, which means the analysis of a manner a person does something, and therefore this approach is motion-based only. Although visual-based methods perform extremely well nowadays, their performance is degraded severely under unconditioned scene properties. For example, in the case of face recognition, the performance of state-of-the-art algorithms is declined due to bright scene, dark scene, random noise, and most recently, masks covering half of the face. As the name of the work suggested, we focus on typing style as a clue for behavior. To realize what a motion-based identification approach can offer, here is a little quiz. Are we looking at an image of the same person? This question is quite hard, as both hands look alike. But once we add emotion information, we can start noticing the differences between the two different people. However, our model doesn't see the hand as an image, but as a set of joints coordinated through time. Now, it is clear that the typing patterns are completely different. Overall, our task is defined as follows. Given videos of m different persons, where each person typed n different sentences, we would like to distinguish between the different identities, according to their typing style, even on videos containing sentences which our model never saw during training. This identification method can be applied for access control and continuous person identification. That way, we can protect our private information far beyond a simple password. Video action recognition is a task of assigning an action label to a video clip. One of the approaches to handle action recognition is skeleton-based, where instead of using the entire RGB information, we extract a skeleton representation in time to predict the action in the video. Unlike our style-based recognition task, action recognition is person invariant, and therefore action recognition of off-the-shelf methods are not enough. In our work, we focus on one class, typing. Then, we explore the class distribution and the manner of how different persons perform this action and try to classify the person accordingly. For learning style-based recognition, we present StyleNet. It is constructed from 10 spatio-temporal graph convolution layers, followed by a learnable downsampling unit and a fully connected layer that produce the identity probabilities. Since our model is a graph-based, first we define an adjacency matrix of the hand where all 21 joints are the vertices and their connections are links. The hand center of gravity is marked by X, and we divide the graph links to 3 subsets. First, self-connections. Second, inward connections, indicating links facing away from the center of gravity. And last, outward connections, which is opposite to inward connections definition. The convolution operation on graph is not trivial as on images. Images are ordered and contain a fixed size of neighbors. On the other hand, graph is unordered and doesn't necessarily have fixed neighbor size, which makes the convolution operation hard to implement efficiently. Previous work suggested the following linear approximation for graph convolutions. A as a graph adjacency matrix. Lambda as the normalization matrix. Yields a normalized adjacency matrix. X is the input to the layer, and W are the learned weights. For a spatio-temporal graph, we simply add one deconvolution layer that operates on the temporal axis. We can stack several spatio-temporal graph convolution layers to consider large regions of interest for the graph convolution operation. Besides the fixed normalized adjacency matrix, it can be beneficial to add another learnable adjacency matrix that is completely data-driven and can be different between the different layers of the spatio-temporal graph convolution layers. That way, the learnable model has a higher flexibility and therefore can better utilize the training data. The adaptive graph convolution layer is consisted of A. A fixed normalized adjacency matrix, B. A learnable adjacency matrix, and C. An attention-based samples unique adjacency matrix. When adding all three matrices, B and C produce a layer-specific adjacency matrix, which is more suitable for the task in hand. A emphasizes the immediate neighbors, that is, the short-range dependencies. B is completely learned, and C is somewhat guiding B in its learning process. The input data is entering the self-attention module that produced the sample's unique matrix. Then, the softmax operation normalizes the matrix, resulting the long-range dependencies, which tend to be weaker, to decrease them dramatically. Therefore, the model isn't able to learn these dependencies, since it never permutes them forward, and in return, no gradients are pushing the model in this direction. In our case, the long-range dependencies are crucial, as the hand is a small structure where each vertex is correlated with all other vertices. Therefore, the concept of long and short-range dependencies is not applicable here. We wish to learn the person's style, and therefore, we need to better emphasize the long-range dependencies of the hand. Previous work suggested the non-local module that refines feature representation by weighted similarity between each feature and all others. As a result, it enhanced the long-range dependencies. Finally, we construct our adaptive non-local graph convolution layer that utilizes the information from all adjacency matrices altogether and enhance their non-trivial long-range dependencies, which are crucial for style learning. We apply our model on the mid-level features to enhance the spatial long-range dependencies. We further utilize a non-local module on the temporal axis to produce better temporal dependencies within the deep features. Since there is no benchmark and no dataset for this task, we created two datasets. First dataset, named 80 typing 2, contains 80 persons, each typed 2 sentences for 10 times. This dataset is suitable for re-identification tasks as it consists of a low variety of different motion patterns and a large variation within these patterns. Second dataset, named 60 typing 10, contains 60 persons, typed 10 sentences 3 times. This dataset aimed for classification on new unseen sentences. In the first experiment, we split 60 typing 10 by sentence type, where, for example, according to the left table, 4 sentences were given to train, 2 for validation, and 4 for testing. Since the model needs to infer on sentences it never saw during training, it needs to learn the style characteristic and generalize to other sentences, which means motion patterns it never encountered. We see that our model indeed succeeded in learning the style characteristic as it achieves remarkable results on the test set with increasing margin compared to other methods when the amount of training sentences decrease. We experimented with 80 typing 10. On the left table, we present our result for classification on unseen sentences in an extreme case where only one type of sentence is available for training. On the right table, we present a different use case, where the model needs to infer on sentences it saw during training, but different videos of them. That is, re-identification task. Clearly, this task is easier than the previous one. We tested our model in a scenario of noisy data. We trained the model as usual, and only during test time we randomly zeroed 0 to 3 joints in random frames. We can see that our model is far more robust to noise, and we can attribute it to our non-local approach, as now the model relies less on certain joints and taking into consideration more possible dependencies. We mentioned before that operating under uncontrolled environment is an essential property of identification methods. While the RGB-based state-of-the-art models achieve good results under controlled environment, their accuracy drops when tested under uncontrolled environment. Our method is far more robust since we operate on lower dimension space, which is less sensitive to environmental conditions. We evaluated our model in a scenario where the 3D coordinates of the joints are given. We see that even here our model is superior to all compared methods. Finally, we evaluated the trade-off between 3D to 2D input data. It is quite interesting to realize that we don't lose much when we only use the simple 2D data. Overall, our contributions are as follows. We presented StyleNet, a neural network for typing style learning. We presented 2 new datasets for typing style learning. We achieved best accuracy rates under controlled and uncontrolled environment, and even in a scenario of noisy input. Last, we introduced a new method for person identification based on its unique typing style.